Hello, this is AP Physics 1 Work Energy Power Homework 4 Fix-A-Post, and the first problem I got wrong was problem 49, or the third problem on the homework. Since I did not entirely finish the problem, I'll just show you how I would solve it. So to begin with, I'll write down the conservation of momentum equation. So initially in the problem, the arrow will have a mass of ma and an initial velocity of vai. The block will have a mass also, but its velocity will be 0 because it's not moving, so we don't have to bother including the block's momentum. Now, when the arrow hits the block, they become one combined mass, so ma plus mb, and this new block arrow system will be moving with a final velocity vf. Now, in order to implement this in our work energy theorem equation later on, we will solve for Vf. So to do that, I'll just divide both sides by ma plus mb on both sides. So if I do that, it's going to cancel on the right side, and then I'll just have to divide ma vai by ma plus mb. So that's going to look like this. Now for our work energy theorem equation, we know that when the arrow hits the block and becomes a block arrow system, that the system only has kinetic energy. However, towards the top of its swing, it will only have gravitational potential energy. So we can write our equation as mgh, where m is the mass of the block arrow system, is equal to 1/2 mvf squared. So now we can substitute for Vf and solve for VAI. So now that I substituted for Vf, the first thing I'm going to do to basically solve for VAI is multiplied by 2 on both sides. So on the left side, that's going to look like this. And then on the right side, it's going to look like this. And then I'm just going to go ahead and square MA and VAI and square MA plus MB because it's going to play into the next step of what we're going to do to solve for VAI. Now, as you can see on the right side, the MA plus MB right here is going to cancel with the MA plus MV squared in the denominator over here. So that's just going to leave us with it's going to basically cancel out the squared term in the denominator. So that'll look like this. Now what we're going to do is we're just going to multiply the MA plus MB on the denominator. And we're going to multiply that on both sides to cancel it out on the right side. So it's going to look like this. Now, basically when I multiply it on the left side, I already have a MA plus MB term, so I can just square that. And then these two will cancel. Now all I have to do is just divide by MA squared, and then when I do that, I can just take the square root to cancel out the squared sign on the VAI, and then I will have how to solve for VAI. So when I do that, it's gonna look like this. And then from here, I can pretty much just plug in and then solve for the problem with using a calculator. And when I do that, I see that the initial velocity that the arrow is traveling before it hits the block is 222 meters per second. The second problem that I got wrong is problem 51, or the fourth problem on the homework. Since I again did not do this problem in its entirety, I will just show you how I solved it. So the key to this problem is to use the conservation of momentum equation. So in our initial state, J has a mass mj and is moving at an initial velocity of vi. The skateboard has a mass ms and is moving at the same velocity as J is, so it will have a velocity of vi as well. Now, in our final state, J still has the same mass as before, but he is now traveling at a velocity of VJF. The skateboard will also have the same mass as before, but it will also be traveling at a velocity of VSF. Now, because the problem is asking to solve for J's mass, we will solve for MJ. So to do that, I'll take this term right here and I will subtract it to the left. I'll subtract it both sides, so basically I'll be moving it to the left. And for MJVI, this term right here, I will be doing the same, subtracting it on both sides, and by doing that, I'll move it to the right. So once I do that, I can just distribute the masses out of each side of the equation. So that's going to look like this. So because we're solving for MJ once again, I'll just divide both sides by the term VJF minus VI. So that way on the right side, the only term I'll have is mj. So that's going to look like this. Now at this point, I could just plug in for the variables on the left side of the equation, and I will get my mass. So when I do that, I get that J's mass is 36 kilograms. So now for the next part of the problem, we have to solve for our change in internal energy. And in this problem, for our change in internal energy, we know that's going to be equal to our change in kinetic energy. So in order to do that, I'll find the initial and final individually, then I'll just subtract final from initial. So for our initial energy, kinetic energy, we can use the equation 1/2 mj plus ms as one term times vi squared. So that equation is going to basically look like this. And because we solve for J's mass, we now have all the variables accessible to us in this problem. So we can just simply plug in now. And when I do that, I'm going to get that for our initial kinetic energy will be 639 joules. Now for our final kinetic energy, we could use the equation 1/2 mj vjf squared plus 1/2 ms vsf squared. So that equation is basically going to look like this. And now when we plug in, I'm going to get for our final kinetic energy will be 694 joules. So like I said before, our change in internal energy is equal to our change in kinetic energy. And that's basically just going to be our final versus our initial. And we have both of those right here. So I'm just going to subtract 694 joules from 639 joules. And our result will be our change in internal energy. So 694 joules minus 639 joules. That's going to equal about around 55 joules. And that will be our change in internal energy.